So let's continue with the second course, and the last session of this is hyperbolic surface and Mirzakhani curve counting with Viveka.
Thank you very much, and thank you everyone for coming back. So today I hope to very least get to the point where I state the most general theorem what we want to prove. But before we get to that, I want to recall the main points that we learned so far. So I think maybe yesterday I lost a few people. It was maybe a little bit confusing. But so I'm going to start by telling you what we need to know to go forward. So yesterday we defined the Thurston measure on ML. So ML is a space of measure laminations. It is these laminations that have a transverse measure to them. But what's important is just that they contain all simple multicurves. And in fact, if I take the closure, take the completion of that set, I get equality. So if you want, you can just think about a space of measure lamination as some topological space that in a precise way is the completion, the closure of weighted simple multicurves. Okay. That's all we need to know for now about what ML is. And on there, we put this measure. So the Thurston measure is a limit of these counting measures. So what are these counting measures? So for every L, so just a number, we do a scaling of the whole thing by L to the 60 minus 6, which is the dimension of MLS. I'm assuming S is closed for now. It's not so important, but let's do that. And then I sum over all ML Z. These are the simple multicurves that have integral coefficients. I'll do the counting measure of that, but I scale each such thing by 1 over L. And then what we did with these train tracks and stuff was just to justify that this limit exists. But for now, let's just assume we know that it exists and just have this as a definition of a Thurston measure. Really what it is that we have these finitely many train track charts, and inside this chart is just the Lebesgue measure on the corresponding Euclidean space. But let's take this for this. But OK, so why do we care about this? Really what we want to do is to count certain geodesics, or see what happens as how the number of them grow as the length bound of them grow. So there's no metric here. This is all topological. But suppose we put, say, a hyperbolic metric on S. And let's look at the unit ball, U sub x, of a space of measure laminations of hyperbolic length at most 1. I haven't yet explained how that one can take a hyperbolic length of measure lamination, but in a few minutes I will explain why. So let's for now just assume we can do that. So this is all measure laminations whose length with respect to hyperbolic metric is at most 1. I should have left myself more space. But what happens if so this is a subset. This is actually a compact subset of ML. What happens if I evaluate or find a measure, ML, of this set? So what is ML of UX? Well, I have the 1 over L to the 60 minus 6. And then I'm counting, I'm seeing how many of these points lie inside UX. Right? I get a 1 whenever one of these is in my set and a 0 otherwise. So it's the number of gammas in MLZ. Remember, this is just a notation for simple multicurves with integral coefficients. So again, it's all unions of simple curves that are pairwise disjoint and can have integral weights. And such that if I take the length after scaling by L, I get at most 1. Right. But this hyperbolic length is homogeneous. So the length, if I scale a curve by 1 over L, the length scales the same way. So if after dividing by L I get length 1, the length of the curve had length at most L. Right. And this should then converge, as L goes to infinity, to the Thurston measure of that ball. And this is some number. And this is usually a number that depends on x. So in Mirzakhani's work, this is a constant that you call b of x. And we will come back to this b of x. It's some constant that depends on the hyperbolic metric. So just, I'm going to continue this picture over here, but let me maybe write something just what the conclusion of this is just if I want to count the number of, so maybe let me write it in Word, integral simple multicurves so things in this set whose length is bounded by L. This is asymptotic as L goes to infinity by L to the 16 minus 6 times b of x. So in other words, just the fact that the Thurston measure exists, which really is just the fact that the Lebesgue measure exists, you can count all simple multicurve with integral coefficients. You just evaluate the Thurston measure at b of x. So it's asymptotic to L to 16 minus 6 times b to x. What I said Mirzakhani's theorem is essentially the same, except I don't want to count all simple integral multicurves. I want to count, say, for example, the connected simple curves. So not the multicurve, but connected, or more generally, maybe all. So, well, most generally was fix any curve you want, multicurve or single curve, and look at this mapping classic group orbit and replace that here. And it should also be asymptotic to L to the 16 minus 6 times unconstant. So in a way, what we've done so far and what we want to do is kind of the same as when we counted lattice points in R2. If we want to count all lattice points inside a ball of radius L, that's one thing. Or if we want to count just the relatively prime ones, then we needed to know the density of the relatively prime ones. And so if I here want to say, so like what we want is, so gamma of some fixed type, gamma node, and length gamma less than L, that's what we want. We somehow need to know the density of this type of curve among all of them. Okay. So that's what we're kind of getting to. But coming back to this picture, so because the other thing we did yesterday was to define currents. So I'm going to call C of S the space of geodesic currents. And we ended by showing that all multicurves, so curves, is a subset, or can be viewed as a subset. We just take, so let me just say what currents are again, even though we don't really need to think of them this way. It's a measure on the geodesic and the universal cover, so say a measure on all geodesics in the hyperbolic plane that are invariant under pi 1. But if we have a curve, a multicurve or curve, we just take its lifts and take the counting measure. Yeah, that's what that is. But as it turns out, so well, first of all, we have this inclusion, right? All simple multicurves lie inside multicurves. But the same thing as ML can be viewed as a completion of simple multicurves. The space of currents can be viewed as a completion of multicurves. So it's not obvious from what I said so far, so let me just say it in words, but then we can just take this as a fact. There's a one-to-one correspondence to geodesic currents, the way I define them, and measures on the unit tangent bundle or resurface that's invariant under the geodesic flow and the geodesic flip. And viewing them that way and using that closed orbits are dense in the geodesic flow, one can prove that these are dense in here. But for now, so what we can, I don't really care that geodesic currents are measures. I just care about there is some topological space that contains all multicurves, and in fact, it's a completion. That's all I really need about currents, because what I want to do, I'm going to study some measures that are supported on curves. So I want to define where are these measures, or sorry, measures that are non-zero on curves. So where is this measure supported? Well, on the closure on the set of curves. That's the only reason why I need this space. But it's a nice topological space. It's locally compact. It's metrizable. It's, since there are measures, it makes sense to add them. It makes sense to scale them with positive scalars. It's actually a cone. So all we really need to know about the geodesic currents is it's a nice topological space containing these. However, I do want to, I said this yesterday, but I didn't really explain it, that in fact we have this inclusion too, that ML of S is inside currents. And for that, I need to use the original definition. So let me start by explaining. Yeah, sorry.
Last time you said that this measure is ergodic.
The Thurston measure is ergodic. Yeah, good point.
Where
It will eventually. Yeah, I'll let you know. Yeah. So but this is an ergodic measure on ML with respect to a mapping class group orbit, mapping class group, with what I mean that the only subset of ML that are invariant under the full mapping class group have either 0 of Thurston measure or full. I mean, it's an infinite measure, so we complement the 0 measure. So let me just give you an idea of why every measure lamination can be viewed as a current. So if we have a measure lamination, its support is a lamination. So that just means it consists of complete simple geodesics that are pairwise disjoint. So if we lift this to the universal cover, H2, so we have a union of non-intersecting geodesics. In general, I mean, unless this is a simple curve, there's infinitely many of these. But yeah, I don't know how to. But they never intersect. And what we have to do is to define a measure on the circle across the circle, or the set of geodesics we can identify with the endpoints. So if I take, it's enough to do it for small open sets. So like say this is A, and I don't know, maybe I can do it a little bit like this. And this is B. And I want to define, so lambda gives you, I'm going to call it the same thing in a current, which assigns to the measure A cross B. If it was an actual simple multi-curves, I would just count the number of lifts that has one endpoint in A and one endpoint in B. If it's not finite, I can't do that. But what I can do is I can find a transverse to all, a little arc that's transverse to all lifts with one endpoint in A and one endpoint in B. And because this is a measure lamination, it comes with a transverse measure, namely measure assigned to every arc transverse to it. So I just define this to be that transverse measure, which may be a bit awkward notation, but just the transverse measure that the measure laminations gives to this arc. And then again, just like I do with curves, I don't give it a new name. I just think of it as being a current. So now we'll think about closed curves, so closed geodesics, or multi-curves being currents, and measure laminations currents. Okay. Questions? So now, before coming back to this counting, I want to give some more facts about the space of currents. But again, from now on, we can just think of space of currents as a nice topological space containing ML, containing all curves. So the first, well, it's really a main theorem in this by Bonahan. I think in his thesis. So if we view curves as currents, when we have curves, it makes sense to talk about the geometric intersection number. Just to say, if you want to take the geodesic representative and just look how many times they intersect each other, that this intersection form actually extends to the bigger space of currents in a continuous way. So geometric intersection number of curves extend to, so I'll call it I, again, from currents times currents into R plus, or greater or equal to 0, and continuously. So we're just going to take it as a fact. It's not hard to describe what it is. What's hard is to prove that it's continuous. So basically, all I'm saying is it makes sense to talk about two currents intersecting, and you always get a finite real number, possibly 0, but never negative, and such that if the curves are, or if the currents are actual multi-curves, it agrees with our usual notion of it. And it's also bilinear, so linear in each coordinate, and mapping class group invariant. Just like the geometric intersection numbers. But from this, once we have such an intersection, one can identify ML of S exactly at the subset occurrence with 0 self-intersection. So ML of S is nothing else but the currents No, so yeah, exactly. So in general, this will be real numbers. Yeah. And I think, okay, so there is something to say that. I mean, I haven't defined exactly what the intersection number is, so it would be hard to explain, but I think it's not, maybe it's not hard to convince yourself that with this picture that if you can approximate any measure lamination with simple ones, so, and the intersection number is continuous, so that should also be 0. But basically, so the support of a current that's actually measure lamination is going to be like a lift of a lamination, so no intersection. Okay.
That's an operator in homology.
Sorry?
That's an operator in homology, I guess, right? So it's something, the intersection number is
yeah, it's defined in terms of integrating the product measures.
right, but then so I guess that you have a transverse homology and that's the
Okay, that's maybe one way to say it, but you don't need to talk about homology to define it, actually. I mean, it's really, so the easiest thing is to see if you want to intersect a curve with a current, where a current might not be one. Yeah. Then what you do is like you take lift, yeah, you take like a little fundamental domain, like one section of your curve, and then you just take all the geodesics that intersect that part and take the measure of that. Maybe that's the same thing, but yeah. I'm happy to talk more about it later. I just don't want to spend too much time on it here. But yeah, so the reason why I write this is because in particular this means that this subset here is a closed subset. Because the intersection is continuous, and this is defined as that's intersection 0. So it's a closed subset of ML. And we have a Thurston measure defined on ML. I can now view it as a measure on space occurrence, just putting it 0 outside of ML. So that's what I want to say. So I can view M Thurston as a measure on currents, but supported on that closed subset. Just make it 0 outside measure laminations. Okay. Another important subset that's defined in terms of intersection are the filling currents. Let me write fill S. These are all currents that intersect, so it's kind of the opposite of measure laminations, are all the currents that intersect every other current positively. So, and we call it, so these are filling currents. So it's a little bit confusing name because you might have heard about filling measure laminations. That's something else. In this setting, a lamination can never be filling because it has intersects itself 0. I use the word filling because it agrees with filling curves. So if you heard about filling curves, filling geodesic is one. If you cut along it, you cut up your surface into topological disks. You cut up all topology. If I view a curve as a current, a filling curve is indeed a filling current. So something that intersects every other geodesics. And this is an open and dense subset. I don't think we will need this fact, but so in a certain way, generically, they are filling. Okay, and the last thing I want to say is also due to Bonahan, that for all x in points in Teichmüller space, but let me say like a hyperbolic metric on S, there is an associated current, and it's unique. We'll call it lambda x. That gives a hyperbolic length of curves in the way that if you take any curve, you intersect it with this current, you get exactly the hyperbolic length of the curve. for all curves or multi-curves. This is, in fact, it's called the Liouville current, and it is the Liouville measure, essentially, defined right way. So the Liouville measure that we heard in Ian Melbourne's talk. And so this is, remember, so for those of you that know what Teichmuller space is, but essentially just the deformation space of a hyperbolic structure on a fixed surface, one can also view that as sitting inside currents. So this is why currents is an important space. It contains all hyperbolic metrics. It contains all measure laminations, contains all curves, simple or not. But the way we will use this is that it makes sense to talk about the hyperbolic length of a current. So we can now define the hyperbolic length of some current by just defining it to be its intersection number with that unique Liouville current associated. So in particular, it makes sense to talk about hyperbolic length of a measure lamination because they're subsets. Okay. Yeah. Exactly. Yeah. Yeah. So you can always add currents, and particularly you can add measure laminations, but some might have intersections. So yeah. Yeah, so let me maybe say something more about this before we go back to counting. So this hyperbolic length function, so we have hyperbolic length. Look at the set of all curves, all closed geodesic on your surface. If you have a hyperbolic metric on it, you have a length function of the curves, just the shortest length of the length of the geodesics. And this here, by extending this length to the set of currents using the intersection, and the intersection by Barnahan's theorem is continuous, that says that this length function extends continuously to the space of currents. So any such function with some mild conditions is called a nice length function. So a length function on curves, so closed geodesics, curves on X, or three homotopy classes on the topological surface S, is nice, a nice length function, if it extends to a function on currents, which is continuous, so as a continuous extension. It's usually the hardest thing to prove, but and we want it to be homogeneous, by which I mean just that the length of C times a current is C times the length of the current for all scalars C, and positive. With what I mean is just that F mu is positive for all non-zero mu. So technically, the zero is the zero measure is a current, and f of 0 would always be 0, but always. Okay, so in particular, hyperbolic length. But there are many other natural metrics you can put on a surface that extend to a length function of currents. So there are many other. So let me give you a few. So you can take any Riemannian metric, say negatively curved, say pinch curvature, for example, curved Riemannian metric. This was proved by Utal. So if you have a negatively curved metric on your surface to each homotopy class, there's a unique geodesic in it, and the length which corresponds to that metric is just the length of that geodesic. And this length function extends to the bigger space of currents in a nice way, continuously, homogeneously, and positively. In fact, you can do this more generally for any Riemannian metric. So we will always have a surface of negative curvature, or sorry, of a negative Euler characteristic. So if you put something that has some positive curvature, it has to have singularities. But so any, so say, singular Riemannian metric, but you're allowing, doesn't have to be non-positive, could have positive places. And I proved this together with Hugo Parlier and Juan Soto. You can also do like Euclidean cone surfaces. For example, what's called translation surfaces or square tiled surfaces, if this is something you've seen. This was proved by Moon Duchin, Chris Leininger, and Kasra Rafi. So for example, if you want, so we say the genus 2 surface can be obtained by gluing an octagon with opposite sides. If you do it hyperbolically, you get a nice smooth hyperbolic structure. But if you do it with an actual Euclidean octagon, you're going to get a Euclidean cone surface. It's going to be Euclidean everywhere except for the vertex where you have axis angle. So that extends to a nice length function on currents. And there are many other of this form, but some more kind of combinatorial, where we completely forget about the metric structure, is you can just take a filling, so a filling current. If you want the filling curve, just it doesn't have to be, I mean, it can be an actual closed curve that is filling in the sense that it cuts up all the topology. And then you can define the length with respect to this of any other curve to just be its intersection. This follows von Banahan's, that intersection form is continuous, so this extends to, this could be in general current. But yeah, so you can define the length of a curve just to be the number of times the geometric intersection with this one filling curve, and then define that as your length, and that extends nicely. Intersection is continuous, so extends continuously. You need filling for this positivity too. Okay. And maybe let me put one more. So yeah, so here again, this is completely just topological. And a more algebraic thing, you can take the word length with respect to a finite generating set. Set of pi 1. So this is also a combinatorial or topological length. So any free homotopic class of a curve is identified with a conjugacy class in pi 1. Its word length is the fewest number of generators you need to write a representative in your conjugacy class. So all of these extend nicely. So why do we care? Well, if we go back to what we started with, that we could count so far just a set of all integral simple multicurves of bounded length. We used this was a hyperbolic length here. That's where x came. But how did we use that with hyperbolic? There's nothing about the hyperbolic metric in the convergence of the measures. So we introduced the hyperbolic metric to define this unit ball. But I could have defined this unit ball with respect to any other of these nice metrics, nice length functions, so maybe u of f, and I replace this with an f. Since it's where I use homogeneity is that the length of, technically this should be f of 1 over L of gamma should be less than or equal to 1, but that because of homogeneity is f of gamma is less than or equal to L. And what I then get is that it converges to the Thurston measure of a unit ball with respect to that metric. So this constant is something that depends on that metric that we're using. So the homogeneity was important for this. The positivity is just so things are actually finite. If we can find measure 0, it could be infinite in here. Continuity is a very essential part of it, which is more hidden. But so let me just say it in words because I not really want to go into the details. If I have that certain measures converge in a weak star topology, and I want to say that that implies that the measures evaluate this set converges to the limit measure of that set, I need to say that the Thurston measure of the boundary of that set is 0, and you get that from continuity. So continuity is, even though it's not completely obvious from there, is an essential thing. So if every length function extends to a thing occur, yeah. So there's some work done on this. So no, it's not true. So actually, I'm also slightly lying. Sorry. When it comes to counting, you can count with respect to any of these the way it says. If I want to actually extend it, in certain cases, for example, this, I have to take what's called the stable length, where I do the length to the power n and divide by n and let n go to infinity. And actually, so if I just did as it is, there can be some problems, but with stable length. So not all length function extends, but there's some work by Didac, Martinez, Granado, and Dull and Thurston that have some conditions for when do they extend, and also examples when they don't extend. So they don't always extend, but they have at least some necessary condition for when a length function extends. Other questions? Okay, so now I'm going to get back to counting. But yeah, again, just to reiterate, the point of this, the extension things here, is to show that there's nothing particular about hyperbolic in what we're doing. It's just, as long as you have a length function that extends nicely to the bigger space, to the closure of a set of curves, you can count with respect to that. Okay. So let's get back to the original problem, where we want to count a curve of a specific type. Maybe I leave that. So maybe I'll remind you what we're doing. So we're going to fix gamma non. A curve or a multi-curve, doesn't matter. Not necessarily simple. Could be, doesn't have to be. And so gamma is of type gamma non if they lie in the same mapping class orbit. Again, that means, for example, if you have if you look at simple curve, it could be separating or non-separating. So that could, for example, be your type. It's not true. Every non-separating curve is of the same type. We saw, I think in my first lecture, that non-separating ones could be divided into finitely many types. But if you want, whenever I say type, you could think simple non-separating, for example, or just all simple, if you want. Or just, I mean, one thing that's very natural that you want to count, if you care about simple ones, just connected ones. So instead of multi-curve, count all simple connected multi-curves, all simple curves. That you could think of that as your type. And what we want is asymptotics of the number of curves of our fixed type, who's, let's say, hyperbolic, but whenever I write the length now, you can choose your favorite length from over there. We want the asymptotic of this. Okay. So we're going to do a thing similar to what we did for the Thurston measure. We're going to translate this into a statement about measures. So we're fixing the gamma non we want to count and some number, positive number L. And we're going to consider ML sub gamma non to be 1 over L to the 6d minus 6. We're going to sum over all curves of that type and take the counting measure, the scaled counting measure of this. So it's a measure on currents. And this is precisely why we need currents. Okay, so what is this? It looks very much like the Thurston measure, but we're summing over something else. Before we summed over all simple multi-curves with integral coefficient. Now we're summing over the type of curves we want to count. If gamma naught is simple, so it's everything we're summing over, and this is actually supported on ML. But if it's not simple, it's supported outside of ML, and we need a closure of where it's non-zero. We need a closure of things of this form, which is or a subset of currents at least. So this is why we need a space of currents. And now, just like we did with the Thurston measure, if we were to evaluate this at the unit ball, so if I use a unit ball as before, let's do a hyperbolic, but again, you can take any one you want. This is exactly 1 over L to the 6d minus 6 times the number of curves of the type we want, such that its length, after dividing by L, is at most 1. So its length is most L, which is what we want the asymptotics of. So if we can say what these converge to, we can do the same as we did with Thurston measure and get what we want. And that is the most general statement of Mirzakhani's theorem. So in the case for simple curves, this was proved by Mirzakhani in our thesis. And then Juan and I extended it to the non-simple case. Namely, so for any gamma naught on a surface of genus G, these measures converge to a constant times the Thurston measure. And this constant can be written as there's a constant that depends on gamma naught and a constant that depends on the genus. I write them as a quotient because this is how Mirzakhani wrote them, and we can say something about what these are. Okay, so this is the main theorem. And this is, okay, so as L goes to infinity in the weak star topology on currents. So Mirzakhani proved this when gamma naught was simple, so she only talked about measure laminations, because in that case, everything here are measures supported on the space of measure laminations. If we allow this to be non-simple, we need to use currents, so then I view this as measures on currents. So something I'm just, let me write what this constant is. Everything can actually be expressed as Thurston volumes. So it's the Thurston measure of, in a sense, the unit ball with respect to length given by intersection with this curve. So this is all measure laminations, lying a little bit, I'm going to say where I'm lying, that intersect the curve, the type, the fixed one that we have at most once. This is true if gamma naught is filling. If this is not filling, this is not finite, because there's a bunch of things that have zero self-intersection with this. So in general, what one needs to do is to quotient out this MLS by the stabilizer of gamma naught. It turns out that this acts nicely, it acts properly discontinuous on this space, and so this quotient is nice. Okay. And let me just write what this BD is without saying much of it. It can express as sum of these kinds of, so for every curve, one has one of these C constants, so C of gamma naught, where we summing over all simple multi-curves, or each type of simple multi-curve. Let me just write this for completeness, but we're not going to talk about this constant. Mirzakhani expressed this constant very differently. What she did is she integrated this constant B of x, the Thurston measure of a unit ball with respect to hyperbolic metric over moduli space with respect to a Will-Peterson form, but that doesn't come up here at all. So our techniques are proving this. So our proof is different even for the case of simple ones, and it's completely combinatorial. That's why we get things like this instead of talking about moduli space and Will-Peterson metric and things like that. Yeah. Yeah.
In the case when you are considering the Thurston norm,
Yeah.
you are divided by 1 over L to the 6G minus 6 because that's the number of integer comes
Yeah.
general. Now you are fixing annual type.
Yeah.
Why you are dividing by this?
Yeah, exactly. So that's not clear if you, at first. So if it's simple, then it is clear, because then it's a subset of ML, which has or it comes also clear from train tracks and so on. If it's not simple, yeah, that's true. Why should we believe that L16 minus 6 is the right growth? So, and that's part of the proof here. But basically what we do is, so we're not looking at all, we looked at fixed types. In particular, we look at those that self-intersect at most k times. Okay. And so if you look at the set of all that intersect at most k times, we do surgery to remove the self-intersections. So we get a map from curves with fixed number self-intersection into simple ones. And what we prove is, so this is clearly not one-to-one, but we prove that generically, as things are very long, it's bounded to 1. There exists a universal constant, so it's k to 1. And that's where that comes from. Other questions? Okay, so just to relate this back, I mean, it's exactly what we've been doing a few times already, but just to make sure it's clear that this means that we can count with respect to any of these nice length functions. So corollary. So for any nice length, and any gamma naught, simple or not, multi-curve or connected, the number f length. This is asymptotic. Okay, so maybe I should explain. This is this m gamma naught of L evaluated at the unit ball. That's what this is. So this in the limit. No, so maybe let me write as limit, but let's put this L to the 16 minus 6 here. Yeah, I needed that for it. So this here is this measure is then equal to C gamma naught over BG times the Thurston measure evaluated at that UF. And this is what in Mirzakhani's theorems is called like B of your metric. B of x in our case because it's hyperbolic, but more general like this. So in particular, the asymptotic growth is a constant, and these are positive, by the way. Otherwise, this wouldn't have much content. So asymptotic growth of the number of things we want to count is asymptotic to a constant times L to the 16 minus 6. That's how I stated the first time. And the constants are this. So it's broken into a constant that depends only on the type, something that depends on topology of the surface, and something that depends on the metric. And basically everything here is Thurston volume of something. Okay. So yeah. So let me just show you. Maybe let me do the following. Maybe let me say, I want to say something about the proof, but it doesn't make sense to try to rush it through in 6 minutes. I want to say something else instead. Let me just say something in words for those of you that are still following. Suppose I wanted to just count a connected simple curve. So that's what I'm summing over here. The type is just all gamma that are simple, closed geodesics. And then I want to look at the convergence of this measure. But this measure is completely bounded by the Thurston or these things that the Thurston measure are limits of. Because here, over there, I'm just counting over a subset of these. Here, I'm counting over all simple multi-curves. There, I'm counting over just some simple curves. So it's bounded by this, and this converges to a Thurston measure. So any limit point of this family of measures is bounded by the Thurston measure. So in particular, it's absolutely continuous with respect to the Thurston measure. And there's where I use ergodicity. If you have something that's absolutely continuous with respect to the Thurston measure, everything by definition are mapping class group invariant. They have to be multiples of each other. And then if it's not a simple curve, you have to do more work. Essentially what I was saying, that you get this map that's bounded to 1, and you can still get that any limit point is bounded by a Thurston measure. And then, yeah. Okay. But let me say, give you a nice consequence that has to do with this constant. So these constants are, to a certain extent, a bit mysterious, but particularly this constant can be computed. Combinatorially. At least in theory. It quickly gets very complicated. But if you have surfaces of not too big complexity, and especially if this gamma naught is simple, even though you can do it for some non-simple too, you can actually write down what this is. You can get numbers for these things. Okay? So then maybe that doesn't seem very helpful because it's just one constant and there's 3 constants there. However, suppose you do the following. So fix, no, how do I want to say this? Yeah, so fix S, so some genus T surface, and 2 curves, gamma 1 and gamma 2. And suppose I wanted to look at the ratio of curves of type gamma 1, whose length with respect to some metric, whatever metric you want, and a nice length function, say a hyperbolic metric, is less than L. And those that are of type gamma 2 on the same, with respect to the same metric. So this is for any, say, hyperbolic. And if you took the limit of this as L goes to infinity, well, they both limit to things like this, where this is the only thing that's different, gamma 1 or gamma 2. So this limits, so remember I write a C gamma 1, B of x over little bg, C of gamma 2, B of x, B of g. So it's just the ratio of these 2 constants, which can be computed. Okay. So, for example, to just give you a concrete thing, and this was done already by Mirzakhani, but oh, sorry, maybe I'm erasing this too early. Sorry. So Mirzakhani did an example of this. If we look at the genus 2 surface, there's actually only 2 types of simple curves. There are those that don't separate your surface. If I cut along it, I don't separate it. So maybe that and this one. So this is like gamma 1, say, and those 2 are the same type. Or I can if I cut along my surface and I separate into 2 pieces, and in this case, the only way to partition 2 is in 1, 1. So there's actually only one type of separating as well. She computed the following. So that the number of non-separating, so things like gamma 1, non-separating gamma, whose hyperbolic length is at most L, divided by the number of separating in the limit, this is 48. Exactly 48. So it's saying that in a sense, so what I'm trying to say, being able to, yeah, there are 2 different ways of seeing this. One is like saying, if I take a random simple curve, if I say, I look at all simple curves on my surface, what is the frequency of non-separating compared to separating? There's 48 times as likely to be non-separating than separating. Or if you want the probability, so if you take closed simple geodesic, on the closed surface of genus 2 at random, so what do we need by random? And I guess this is one of the motivation to actually counting them. If I can count the number of closed geodesic of length at most L. There's finitely many. I can pick one at random and then let L go to infinity. So I get a notion of picking stuff at random. Out of time, let me just write one line. If I pick a simple closed geodesic at random on a genus 2 surface, the probability that it is non-separating is 1/49. And the point here, too, is that it didn't, I used the hyperbolic metric to compute things, but it doesn't matter, it's always 48, no matter which hyperbolic metric I took. So, and other people took advantage of this and generalized it, actually using different methods, but Delacroix, Goyan, Anton Sorich, and Sograf, they vastly extended this to notice that, so if I take a genus G surface, I can again compute this, and I get some number that doesn't depend on a hyperbolic metric, just on the genus, and that letting the genus go to infinity. And then they proved that if you take a random closed simple geodesic on a random surface, in the sense that any genus, then the probability that it's non-separating goes to 0 and exponentially fast in the genus. So the way we draw, or the way I usually draw hyperbolic surfaces like this, is very much not what hyperbolic surfaces should look like. It should be very difficult to separate your surface. If you draw a simple closed geodesic, it's most likely going to stay connected if you cut them on it. Okay, so let me end there.